The Dynamic Host Configuration Protocol, or DHCP, is a network protocol used to automatically assign IP addresses to hosts. This mechanism is particularly valuable for managing IP address allocation efficiently and helps mitigate the shortage of public IPv4 addresses. DHCP operates over UDP using port 67 for the server and port 68 for the client. The DHCP process involves 4 key messages. It begins with the DHCP discover message, where a client with no IP address yet uses the source address 0.0.0.0 and broadcasts to 255.255.255.255 to request network configuration. This message includes a transaction ID to track the exchange. In response, the server sends a DHCP offer message that contains the same transaction ID, the server's IP address, and again a broadcast destination address. It also includes a proposed IP address for the client and specifies the lease time for which this address will remain valid. Continuing the DHCP exchange, the client responds to the server's offer with a DHCP request message. In this message, the client reuses the transaction ID and still uses the same source and destination IP addresses used in the previous step. It specifies the accepted IP address from the server's offer, identifies the server, and echoes the proposed lease time. Finally, the server completes the process by sending a DHCP ACK message. This confirms the assignment, reiterates the transaction ID and lease duration, and officially assigns the host the offered IP address. The destination remains broadcast, ensuring the client receives the confirmation. Here we see the complete DHCP message exchange between a client and a server. The process begins with the client broadcasting a DHCP discover message on UDP port 68, asking any available server for an IP lease. The server responds with a DHCP offer, suggesting an IP address and providing its own address, along with the lease time of 3,600 seconds. The client then replies with a DHCP request, confirming that it wants to use the offered address. It again broadcasts the message, echoing the server's offer and requesting the lease. Finally, the server sends a DHCP ACK to confirm the assignment. It uses the proposed IP as the destination, includes the lease duration, and completes the address assignment. This 4-message exchange dynamically configures the client with an IP address and essential network parameters. Network Address Translation, NAT, allows organizations to map many private IP addresses to a few public ones. This is particularly useful for conserving public address space. When internal hosts with private IP addresses want to communicate with external servers on the internet, NAT modifies the source IP address in the packet headers. As shown in the diagram, packets from different internal hosts are sent to different external destinations. The NAT device replaces the private source addresses with the public IP and tracks these mappings in a NAT table. This enables multiple internal clients to share the same external IP without conflicts, provided their destinations are distinct or ports are differentiated. However, NAT does not support unsolicited incoming connections from the internet to internal hosts, which limits peer-to-peer communication. For such connections, a non-private IP is always necessary. With NAT, the number of simultaneous communications to the same external destination is limited by the number of available public IP addresses. Specifically, if there are k public addresses, then up to k concurrent flows can be maintained to the same destination IP. This is because NAT must maintain unique mappings between private internal hosts and public-facing identifiers. However, NAT introduces a few important limitations. If 2 hosts from a private network attempt to access the same application on the same external server at the same time and there's only one public IP available, the NAT device cannot distinguish between the sessions without additional mechanisms like port mapping. Similarly, a single private host cannot establish multiple sessions with different services on the same external server unless the NAT can differentiate based on ports or protocols. In the illustrated example, the NAT device maps internal source addresses to the single public IP. If multiple sessions target the same destination and port, the NAT may run into mapping conflicts, making simultaneous communication to the same external service problematic. NAPT, or Network Address and Port Translation, extends basic NAT by including port numbers in the mapping. This enhancement allows multiple private clients to share a single public IP address while still being able to communicate simultaneously. even with the same external server and application. It works by assigning a different source port number for each outgoing connection. This way, even if two internal hosts try to access the same destination IP and port, the NAT device can distinguish their sessions using these unique port numbers. In the diagram, for instance, hosts with private IPs are both contacting the same IP address on port 80. Internally, their original source ports are 9380 and 7409, but the NAPT translates both to the same public IP using different public source ports, 25000 and 25001. This mapping stored in the NAPT table ensures each return packet is correctly routed back to the originating host and application. When a host needs to send an IP packet to another host on the same local network, it must first know the corresponding MAC address. That's where the Address Resolution Protocol, or ARP, comes in. ARP provides the dynamic mechanism to map an IP address to its matching hardware address. In this diagram, we see two hosts, A and B, with their IP and MAC addresses. When A wants to send a packet to B, it doesn't yet know B's MAC address. It sends an ARP request across the local network, essentially asking, "Who has IP B?" B replies with its MAC address, and A stores the result in its ARP table for future use. These tables, shown in the center of the image, are built on the fly by each host and updated dynamically as communication happens. This mapping between IP and MAC is fundamental for Ethernet-based networking. The ARP is essential for translating between network layer IP addresses and link layer MAC addresses. Anytime a device wants to forward an IP packet over a local network like Ethernet, it needs to know the MAC address that corresponds to the destination IP. ARP provides this function. When a host needs to send a packet, it checks its ARP cache to see if it already knows the MAC address. If not, it broadcasts an ARP request over the local network. The station with the matching IP address, the target, responds with its MAC address. That response is stored in the ARP cache or ARP table, so future packets to the same destination can skip the broadcast step. This mechanism is used by both hosts and routers, and it supports both direct forwarding when the destination is on the same local network and indirect forwarding when the next hop is a gateway. ARP operates entirely within the local subnet and plays a key role in the low-level operation of IP-based communication. Here we see the ARP request process in action. Host B wants to send a packet to host A, but it only knows host A's IP address, not its MAC address. So host B constructs an ARP request where the sender's MAC and IP addresses are included, but the target's MAC address is unknown. The destination MAC is set to the broadcast address, ensuring every host on the local network receives it. The ARP request is broadcast across the LAN. All devices see it, but only the one with the matching IP, host A in this case, responds with its MAC address. This reply allows host B to update its ARP cache with the mapping between IP and MAC, so it can now send frames directly to host A. This dynamic mechanism is essential for resolving IP addresses into hardware-level addresses in real time, making packet delivery possible within local networks. This image illustrates the ARP reply phase. After host B broadcasts an ARP request, host A recognizes that the target IP in the request matches its own. Host A then responds with an ARP reply message, which includes its MAC address. This reply is sent directly to host B, not as a broadcast but as a unicast message. The Ethernet frame now has host A's MAC as the source and host B's MAC as the destination. Inside the ARP payload, we see that the sender IP and MAC are host A's, while the target fields now contain host B's information. Upon receiving the reply, host B updates its ARP cache with the IP to MAC mapping of host A, completing the resolution. Host B can now send packets directly to host A at the data link layer, enabling end-to-end communication on the LAN.